This is an integral, so I need to introduce an integration variable. So basically this is q tau in the tau. Let me think if it is correct. Yeah, this is correct. And I think so, but I will just check later on. And then I have the integral between 0 and t of 1 over k e to the power of tau over k p tau in the tau. So you may see that I introduced the variable tau, which is still a time, but it's the variable of integration, okay? And I think it's also tau here, sorry. So basically we have time which is varying between 0 and t, and the generic time varying between 0 and t is indicated by the symbol tau, which is the variable of integration. And therefore everything is variable in time here. I need to indicate with tau, okay? And q, of course, is varying along time, but also the time index of e, the time exponent of e, is varying. Okay, now it's very easy to compute this first integral because it's equal to the argument of the derivative. So basically, now I need to delete here. The first integral is equal to q tau e to the power of tau over k, computed between 0 and t. Because once that we found the integral, we have to compute it between the two extremes of integration, which are 0 and t. And this is equal to the second one is unchanged. I just want to integral between 0 and t. I just put precipitation before e. So it's integral between 0 and t of 1 over k p tau e to the power of tau over k in the tau. So I'm not solving the second one so far. I'm not solving the second one because in order to solve the second integral, I need to give a shape to the function p tau, which is in general not given because precipitation is observed, but it's not characterized by an analytical relationship. So the second integral, in order to solve it, I need to specify a shape for the precipitation over time, and this shape is called the yetograph. Basically, the graph of precipitation is called the yetograph. But in any case, it's important that you get that in order to compute this integral, I need to give a shape to this analytical function p tau, which I don't have so far. So I'm not computing this integral for now. Okay, so instead I can compute on the left-hand side this quantity at the two extremes of integration. So let me do that. Everything is also reported here. If you go down, maybe that there are less steps, but everything is described here. There are less steps because, of course, I made more steps on the blackboard, but everything is described there. I'm just checking whether I used the same symbols. I hope so. Yeah. Okay. And then let me compute here. So basically, Now I have to substitute 0 instead of tau, and t instead of tau. So basically the first thing that I have to do is to substitute t instead of tau, and I get qt times e to the power of t over k minus, now I need to substitute 0 instead of tau, and I get q0 e to the power of 0, which is 1, so nothing, okay? Equal to, again, the integral, unchanged. Integral between 0 and t of 1 over k, p tau, e to the power of tau over k in det tau. Okay. Perfect. Now, given that I want to get an expression for q t, it's better if I divide everything by e to the power of t over k, because I want to get an explicit representation for q. Okay, no problem. So let's do that. Please keep in mind that this demonstration, I may ask it at the exam, because it looks like it is complicated, but I am sure that once that you dedicate some time, you will see that it's not complicated at all. It's just a matter of not losing anything during these steps, but it's not complicated at all. You see that I'm just multiplying and dividing by given quantities, and I'm computing very simple analytical integrals. So, as I said, let me divide, and then I get qt equal to, finally, let me write qt equal to, so basically, this is given by the integral between 0 and t. Keep in mind that e to the power of t over k, once that you gave a sign t is a constant, okay? It's not tau, it's t. T is fixed because it's the time at which you want to compute the river flow. Of course, you can make the computation several times. If you want to describe the hydrograph, you need to make the same computation several times. But each time that you make this computation, t is fixed, so it's a constant, okay? And therefore, I can bring this e to the power of t over k inside the integral sign, because it's constant. So let me bring it inside. So it's 1 over k, p tau, which multiplies e to the power of tau over k, times e to the power of minus t over k. Minus, why? Because I should divide. So the exponent, I just changed the sign to the exponent in order to divide. In the tau, plus, I have a plus here, let me divide, plus what? Q0, which multiplies e to the power of minus t over k. It's divided. Now, we are almost there. Let me delete this one. And now I'm just rearranging everything. So let me write qt is equal to the integral between 0 and t of 1 over k times p tau And now I have this product, which is a product of two quantities which have two powers with the same base E and different exponents. So this product can be written by just one factor with the same base, and the exponent is the sum of the exponents. So basically it's the sum of the exponent is tau minus t. But let me change sign and write t minus tau. This is just for convention. I'm changing sign and writing t minus tau. Minus tau. It's for convention, because on the textbooks they prefer to put t before tau. And therefore in the textbook you find this with the negative sign. It doesn't matter, it doesn't change anything, but it's just a matter of respecting the previous conventions in the tau. Plus Q0 to the power of times E to the power of minus T over K. Look, Q0, it's your initial condition. That's it. With the only problem that we cannot solve this integral. But we now introduce an assumption and solve it. So basically this is the classical relationships that gives to you the means to apply the linear reservoir model. What do you need to do at this stage? You need to know the input data, precipitation, PT, rainfall, and then you need to know the initial condition, and then this integral can be solved through a numerical integration, because you can divide the computation, you can apply this computation at each time step, and at each time step we will see tomorrow is easy to compute Qt through a numerical integration, but we will see tomorrow at the VC. We will do it tomorrow, okay? We don't do it now because at the blackboard is much more complicated than on the computer. Okay? Now, let's assume that Q0 is equal to 0. Q0 is equal to 0. Why is that? Just for simplicity, and also the same assumption is taken here, just for simplicity, because now I'm going to propose a numerical integration, an analytical integration, and for the analytical integration I need to, it's simpler if I assume that Q0 is equal to 0. Okay, so if we assume this, of course, this term disappears. And now, as I said, I need to give a shape to the function p tau. And let me assume that p is constant. This is, of course, the easiest way to define an analytical shape for precipitation. I can assume that precipitation is constant over time. It's already constant over the catchment, so it's spatially constant. But now I am assuming that it's also constant in time. Perfect. So basically, if I do that, what I can write, I can rewrite this relationship in a very simpler way. Basically, what I can do is to write Qt is equal to, I can bring 1 over k times p out of the integral sign, because everything is constant, times the integral between 0 and t of what remains. And basically what remains is e to the power of minus t minus tau over k in the tau. like it's done here. But we can also make a further step forward, because it's better to split this product into a variable term and a constant term. So let me better explain. So let me rewrite this term as a product. So let me write Qt is equal to P over K, integral of what? Integral of e to the power of tau over K times e to the power of minus t over K in the tau. Basically, I'm bringing it to the form that it had before. Why I'm doing that? Because this is constant, and then I can bring it outside of the integral sign. So let me write again, Qt is equal to P over K, P over K e to the power of minus t over K times the integral between 0 and t of e to the power of tau over K in the tau. And now it's very simple to solve this integral. So what I can do basically is to write that Qt is equal to P over K e to the power of minus t over K, which multiplies, the integral is K e tau over K computed between 0 and t. It's easy for you to see that if you take the derivative of this term, you get e to the power of tau over K. And now we just have to compute it between 0 and t. So Qt is equal to P over K e to the power of minus t over K, which multiplies K to the power of e to K times e to the power of t over K minus K. Okay, so by dividing by K, I can write Qt is equal to P e to the power of minus t over K, which multiplies e to the power of t over K minus 1. And so you can easily see that we can simplify this equation in this form. Qt is equal to precipitation, which is constant, which multiplies 1 minus E to the power of minus T over K. So this is our solution, which I am highlighting now in red. This is the analytical solution we looked for, of course, under the assumption that rainfall is constant. And it's interesting to see how the hydrograph looks like. So let's try to depict this function. We put time as independent variable and the river flow Qt as the dependent variable. And we know that at time 0 it starts from 0. So we start from here. At time 0, Q is equal to 0. And let's identify here on this graph the value of P. So let's suppose that it's here. And remember that P can be represented here because it has the same units than the river flow. So we can represent the P value, which is constant over time. So let me write it. So we already said that for time equal to 0, Q is equal to 0. In fact, you see that for time equal to 0, between the square parentheses, you get 1 minus 1, which is 0. So this is fine. And what happens for time tending to infinity? If time tends to infinity, basically, this second term, e to the power of minus t over k, tends to 0, which means that you have the square parenthesis tending to 1. It means that Q tends to P. So you get something like this, asymptotically, which is physically reasonable, because if you get a constant rainfall which doesn't tend, then you can imagine that you start from a river flow of 0, and then you move forward to a condition where you have a very high water storage into the catchment. And therefore, you move forward to a condition where the catchment is saturated. When the catchment is saturated, all the rainfall is converted into river flow. So it is physically reasonable that if the catchment is very wet, you get a river flow that is close to rainfall. This is what happens when you get extreme floods. You have all the rainfall converted into river flow. So this is what happens here. And of course you may be not familiar. You may think that this shape of the hydrograph is not realistic, because you would expect a falling limb of the hydrograph after a while. Instead, here you see only the rising limb. The reason is that we assumed constant rainfall. Of course, what happens actually, so let me delete here. What actually happens, even if one gets constant rainfall, what happens is that at a certain time, rainfall stops. So basically, let's suppose that, let's make this horizontal axis longer. Let's suppose that at time t star, rainfall stops. So what happens here? Because you may say at this stage, I cannot recognize this situation in my equation, because our equation was, let me write again here, Qt is equal to P, which multiplies 1 minus e to the power of minus d over k. So you could say, what happens then? Can I use the model, the linear reservoir model, to reproduce this situation when the rainfall stops? So my reply would be no, you can't use it because we assumed constant rainfall. So basically, if you want to represent this situation when after a certain time of constant rainfall, then you get no rainfall, you have to restart the simulation. You can still use the model, but you have to restart the simulation because you can compute the simulation up to time t star by using this representation here. And basically, you can do that because rainfall is constant. Then, if you get to a point where rainfall becomes not constant, the job of this model is finished, and then you have to start again. So let's start again from here. And we can apply the model from here, but of course, if we have null rainfall, then we have to apply the model by using the initial condition properly. And the initial condition should say that, let's suppose that this value is qt star. The initial condition should be, if I restart again, let me suppose the initial condition, let me call it again q0, should be equal to qt star. And so I should go back to the previous equation, because I cannot assume that the initial condition is given by 0. Okay, and basically, if you go back to the previous representation of the model, not this one, the representation with the integral, you would say that the integral is 0 because there is no rainfall, and you have the river flow that is given only by the initial condition, the developing of the initial condition. So this would be q t star times e to the power of minus t over k. This is what you would get if you go back to the previous formulation of the model. So, what is this? It is a falling limb, a recessing limb, which has a shape like that. And it goes asymptotically to 0. This discussion is not extensively reported here. I just integrated to get the model in this form, and I'm not discussing the shape of the hydrograph in graphical terms. And I may be that I update the lecture by including also a graphical representation like this one. So far it's not included. In general, keep in mind that the web description of my lectures is always more synthetic. There is everything, but of course, while lecturing, I add some further considerations. Now, I want to make some discussion with you about the k value. I said that k is a parameter, and you understand that by saying that it's a parameter, I am implicitly I am implying that we need to estimate it. And we need to estimate this parameter in order to adapt the model to the considered catchment. We will discuss calibration in a while. But let's discuss about its significant meaning. So what happens if k gets very large, and what happens if k gets close to 0? So remember that basically k, we introduced it by saying that the river flow is given by the discharge divided by k. So what happens if k gets very large? If it gets very large, it means that you need, you know, the river flow is very small. And you get a very huge storage into the basin. So if, again, if K is very large, you see that the river flow gets reduced, which means that you get a huge storage. And of course, with a huge storage, at the end, you get an increasing river flow, but into the basin, you have a very significant storage. Conversely, if K is tending to 0, you tend to get a very large river flow, which means that the storage is very low. Because, of course, you have a lot of, it's like the dimension of the discharge of the hole in the tank. If you have K very small, it means that the hole is very huge. So everything it rains into the tank flows out, and you have no storage. If K becomes large, it means that the hole is very small. So you get less flow and more storage. So K is connected to storage. If you are a catchment that stores as a lot of potential storage, then you can imagine that the catchment has a large K. Conversely, if you have a catchment that is fastly responding, like an impervious catchment, so you get rain and soon after you see the river flow, it means that you have reduced the storage and therefore you expect a low K. And if you think that K is a time, it means that for a large time, a large K, so a large time, you have more storage. For a short time, you have less storage. And for a short time, you have a more rapid response. So the response of the catchment, when K is small, is rapid. Conversely, if K, which is a time, is large, the response is slower. So you could think of connecting in some way K to the time of concentration of the catchment, which is sensible indeed. Basing on the reasoning that I just made, it's sensible to connect K to the time of concentration. In fact, there are analytical proofs that demonstrate this and try to demonstrate under certain assumption what is the relationship between K and the time of concentration. And basically, I'm not going into the details of these demonstrations, but we can say that K is about 0.71 times the time of concentration. So if you have an idea of the time of concentration of the catchment, you can get a guess estimate for K. And conversely, if you apply the linear reservoir and you get an optimal value for K, you can get a good guess estimate for the time of concentration. So if we look at this graph, what happens here? So I may ask you, let me draw two curves, and you tell me what is the largest K value. So I draw a green curve. So it is, this is K1, and this is K2. So the red curve has K1, the green curve K2. So my question is K2, and here there is a sign, minor, greater, K1. So K2 is larger or lower than K1?
Larger.
No.
Lower.
Can we make a pool? So who says larger? Nobody, okay. No, I think it is lower because this is a more rapid response. So K is lower. Because you see that you converge to rainfall quickly or in a quicker solution.
Okay, if the vertical graph is QT, yes?
The vertical axis QT.
So
QT or rainfall constant rainfall can be represented
Okay.
here. Okay. Okay. Good. Now, a few words about calibration, and I still have to write the lecture on calibration. I'm planning to write next week a separate page on model calibration, because calibration is a cross-cutting subject. So we can use calibration, we can calibrate a rainfall runoff model, but we also have to calibrate sometimes rainfall models, infiltration models. So calibration is a different subject, but I want to anticipate some considerations. Before illustrating to you the next rainfall runoff model, I want to anticipate some considerations on calibration, because tomorrow I would like to propose to you an exercise of application of the linear reservoir, and I hope that we can calibrate the parameter K. So let me, and the exercise is still not here, let me see, I don't remember, but I don't think, oh, sorry. It's the other page, so I will check, but in any case, tomorrow will be there. So how can we calibrate the parameters for a model? So model calibration. And let me talk about a particular case of calibration, which is matching